Hey everybody, so today we're going to be doing a video on how to do asymptotic runtimes of recursive functions. So in the last video we did iteration, and our strategy there was we made, do I still have it up? Yeah. Our strategy there was we made a chart of iteration number versus work at iteration, and then we summed up the work at iteration over all the different iterations. So when I was 1, I was 2, and then for this particular problem, then 4, 8, 16, and so on. But maybe in a different problem, it would be I equals 1, 2, 3, 4, 5, etc. And that's problem dependent. Okay, and so for recursive functions, we're going to do something pretty similar. We're going to, instead of doing it per iteration, we're going to do it per call of the function. And that's where we'll create these trees that you might have seen in discussion or maybe in lecture. So let me show you the 3 things you need to know before you can make the tree. Okay, so the 3 things. Number 1, you want to know the reduction in problem size. So the reduction in, I'm going to say PS. I don't have enough room to write problem size. Okay, the second thing is, and I feel like I've written this in a different order. The order doesn't matter at all. It's just, I guess maybe I could have done bullet points instead. But okay, the second thing we want to know is the work per call of the function. And we'll go over what all these mean in a second. Work per call. Okay, and the final thing is the branching factor. Branching factor. And once you have all of these 3 things, then you can create your tree. So here what I have written is a general form of a tree recursive function. And the reason, and you might remember tree recursion from 61A, and this is one of the reasons why it's called that, because it sort of creates this tree effect, right? So if I had a function that called itself twice, then it would sort of look like a binary tree, like this, and so on. Okay, so in this case, let me annotate the different things we have. So the reduction in problem size, I guess I can underline that in red. And here, that is this function Rn. Okay, now let's look at the work per call. Here it's G of n. And now, for the branching factor, here it's B. So, go back to the black. So, generally, like what this function, what all recursive functions will be doing is they'll do some amount of work per iteration. Not per iteration, per call. That's this G function. So maybe G, and maybe they don't call a function. Maybe they do like a double for loop or a single for loop, or they just do something that takes some amount of work, okay? And then now let's look at the reduction in problem size. So they might not call a function R. Maybe commonly what you'll see is like something, for the recursive cases, they'll just do f of n over 2, or maybe f of n minus 1. So that maybe they don't actually call the function, but you can kind of wrap it in its own function when you do your analysis. Okay, so that's those 2 things. And the branching factor, that's commonly just how many times you see the recursive function. So for example, in the Fibonacci function, you see something like this. You see fib of n minus 1 plus fib of n minus 2. And in this case, since there's 2 fibs, the branching factor is also 2. In our case, we kind of wrote it in a little bit of a weird way. We have like this loop which calls it many times. In this case, it calls it exactly b times. And so most likely it's not going to be a loop in a problem you'll see. They might just write it multiple times, like 2 times or 3 times. So in this case, b is a constant. It's like kind of baked into your function. It's not a variable. It could be a variable, but for now we'll just ignore the case where it's a variable. Okay, so let's actually write out an example, or actually first let's do the general what the tree should look like. Okay, so first the tree is going to have the initial problem size. In our case, it's n. So n. Okay? And now, how many children will this tree have? It'll have exactly b children. So I'll do that. And each one of those children nodes is going to look like the value in that node is going to be r of n. And that's repeated for all of these. Okay, and this keeps going. So the next level would be r of n, right? Because you're going to apply this reduction, that reduction right there, you're going to apply that to this node now. And so you're going to do r of n, where n is now this r of n, so now you get this double r of n. So, for example, let's say r of n equals 1/2 times n. Then what you might have seen before, this would be n, this would be a half n, and this would be a fourth n, right? Or maybe r of n equals n minus 1. Then that would still be n, this would be n minus 1, and this would be n minus 2. So those are just two examples of r of n. Note that they're both decreasing in the input, right? And that makes sense because so I guess increasing the input definitely does not make sense because then this function would never reach the base case, right? In this case, the base case is just 0. Typically, you can kind of ignore this. It doesn't really have an effect on many things because it's just equaling some constant. Okay, so this is what your tree looks like, and eventually it goes down to whatever the base case is. Let's just pretend it's always 0. Shouldn't really matter. Okay, and that's what your tree looks like. And now you want to figure out how much work does this tree do. And this is where it kind of is problem dependent. Depending on what your problem looks like, there might be a better or worse way to approach finding the sum of this tree. And so let's go over the different ways there are to figure out the sum of the tree. Let's write this, if work per level is constant, and I guess another important thing, actually I did not write, is the height of this tree. So I'll just denote as h, and then we'll talk about different ways to figure out the height. Okay, so if work per level is constant, then what should you do? You should do h times, I'll call it WL, where L is the work per level, which we just said was constant, right? For number 1, work per level is constant. Okay, so in that case, then you should do h times WL. And why does that make sense? Well, if every level does the same work, then, okay, so that's WL, that's WL, that's WL, and you'd keep going. And I put a line here. I really should have put ... The height might be multiple different levels, right? So ... until WL at the bottom level. And since there's h levels, each level does WL work. The total work is h times WL. Okay, so that's nice. Let's scroll down a bit. Now let's talk about a different scenario. Maybe the work per level is not constant. If it's not, or actually let's talk about if the work per node or also work per call is constant. This is one of the easier ones as well. If every node/call to the function does the same amount of work, and again, remember the work per call, that was that g function earlier. It's this g function up here. If that's constant, as in it's the same for every single node, then what we can do is we can just count the number of nodes in the tree. And that's easy. Well, if the tree has height h, and each one of these, and the branching factor is b, then we can write that out. It should just be b to the power of h. I'm gonna box these things so we know. Then it's just b to the power of h. And so, for example, one thing to kind of sanity check this is if we had a binary tree, right, we had something like this. And it keeps going to the bottom. We have a bunch of really long row here, where the height is h. Then the total number of nodes in this tree is just 2 to the h, right? Okay, and that's what this would have said too. Let's remove this. Okay. Okay, the other scenario, the last one, is if the work per call is not constant and the work per level is not constant, then you'll just have to write out a summation. So I'll just write else, write out summation, where each term corresponds to a level in the tree. Okay, so these are okay, I guess what I mean by that is, for example, let's say you figure out that, let's see what that look like. That would say, so then your sum, I'll say that work total is going to equal, well, the first level is this one where it's just n. How much work does that node do? It's g of n. G of n plus, well, the next level has how many different things? It has b different things. Oh, I guess maybe we can write that there. B branches. The next level has b different things. So it's going to be b times any individual work of those, because they should all be the same, right? I guess that's one assumption we made, is that they're all the recursive calls are on the same reduction size. Okay, so now it's going to be b times the work function, but now instead of n, it's going to be r of n, right? Because we went down a level, we're going to one of the node's children, and so the reduction size says we should go, our new value is r of n. And then it's going to be plus b squared times g of r of n, and so on until the bottom level. And the bottom level would be b to the h times g of, in our case it was 0, maybe in your case it's 1 or 2 or something like that. It shouldn't matter. It should this should almost always just be 1. But okay. So yeah, okay, so now let's try to apply this to an actual problem. So let's fill in some values. Let's say that, what colors did I use? I said, okay. Let's say this equals, or not equals, but is, not quite equals, but is theta of n. Let's say it's linear time. Okay, and then let's say that the reduction is n over 2. Okay, now let's say that the branching factor is 2. Okay, so now I've just filled in these 3 values, and now this uniquely identifies the runtime of the function. Okay, let's look at that. Let's figure out what it looks like. So looking at this tree, I'm going to copy basically this tree except plugging in our values. So where's our, here we are. Actually, let's do it down here. Okay, so the top node is n, and then the next node is the reduction in the problem size. And remember, it was n over 2 for our case. N over 2. This is, I guess I could have drawn it better. N over 2. And then it would be n over 4, but I don't have enough space, so I'm not going to write it. And the bottom layer is going to be a bunch of zeros. Or ones, right? It doesn't really matter. Okay, and how much work does each node do? Let's check. What was our g? Our g function said it was linear. Okay, so that means that this top node, this does n work. This does n over 2 work. This also does n over 2 work. And now we're just going to figure out what strategy should we use. Strategy 1, if the work per level is constant. 2, if the work per call is constant. Or 3, otherwise. Okay, let's check the condition for strategy 1. Is the work per level constant? The first level does n work, okay, and the next level does n over 2 plus n over 2 equals n work. So it seems that the work is constant, but let's just double check. If we went one further level, then there's going to be 4 nodes, right? Because I have these 4 branches here. 4 times. And what's the work going to be for an individual node on that level? It's going to be n over 4, right? Because if the previous one was n over 2, then the next one should be n over 4. Okay, and that cancels out nicely, and we get n. Okay, so it does seem that the work per level is constant. Okay, so we're just going to do whatever that first formula was. Height times WL. Okay, so we know WL, that's the work per level. It's n. Now we just need to figure out the height. Okay, so we know that WL is n. Now, what's the height? Well, the height is just, however many times we need to divide n by 2 to get to 0. And at first, that might not make sense because if n is positive, then no number of divisions can make it equal 0. So you might say infinity. But because we're not working with real numbers, we're working with Java integers, at some point you're going to have something like 1 divided by 2. In Java, this equals 0 because remember that if you divide 2 integers, you're going to get an integer back, and it's going to floor the result. So even though this equals 0.5, because it's of type integer, Java's going to say, okay, I'm going to ignore the fraction. That's 0. Okay, so another way of saying, so we picked 0 here. Another thing we could have done is just say it's 1, and that would make it easier for the calculations. So here's the sequence of node sizes. So the first, at level 0, it's n. And then the next level, they're all going to be n over 2. And then it's going to be n over 4. And this is going to keep going. And then, like we said, we can just put 1 here instead of 0. Because they're basically the same number in terms of when we're doing runtime stuff. They're so, the numbers we're dealing with are so big, a difference like that is negligible. OK. How many numbers are there in the sequence? This is, I guess, another definition that you should memorize. This is just the definition of log of n. Okay, so we know that the height here is log of n, because that's the, right, if you kind of take this sequence here and make it vertical, it directly corresponds to each level. So this is level 0, level 1, level 2, and that's the last level. Okay, and then we just multiply these, right? That's what our formula said. It says you do h times WL. So that means this is theta of, and it's theta because the g function we saw, g is theta, so then that means this function is also theta. If it was omega or O, then we would use that bound. Okay, theta of, what did I say? N times log n. Okay, yeah, that concludes this video. I highly suggest that you try a problem that looks like number 2, or that you can use the number 2 formula on. So let me write numbers that would give you that. So g of n is going to be constant. B is going to equal, let's say, 3. And then r, let's make it equal n over, or let's just say n minus 1. N minus 1. So try these, and then you should be able to apply number 2 out there. And then you can take what we've covered here and apply it to any kind of recursive problem you see. So yeah, that concludes this video. Can't really zoom out too much, but in case you want to take a screenshot or something, cool. That's about the best I can do. Yeah, so okay, I'll see you all in the next one.